This next hour, we're going to review logistic regression. Okay, I'm going to do a quick review of the odds ratio. Okay, because odds ratio actually estimation is a really good product or result from logistic regression. Right? So I hope you remember the odds ratio. And if you look at this contingency table, we have the role factor, right? That's a risk factor, whether you're exposed to risk factor or not. So yes and no. And usually when we do the coding, right, because it's logistic regression is actually for modeling binary response variable. So your binary variable, response variable has two categories, and it's categorical, yes or no, right? And we use an indicator variable for that, sort of, right? One indicate yes and zero indicate no. Okay. So for the role factor or risk factor, we have yes and no, and then disease status, whether they have disease or not, right? One for yes, zero for no. So we have an indicator variable, disease status, one's take on yes and zero takes on no. So I hope you understand the meaning of indicator variable, similar to what we mentioned earlier. So this is a day that we have 300 subjects, 70 of them exposed to risk factor, 50 out of these 7 have disease and 20 no, and 230 didn't expose the risk factor, and 100 of them have disease, 130 no, right? So with a table like this, of course, you can calculate odds ratio, if you remember what odds ratio is, right? So you have yes and no's exposed to or not exposed to the risk factor. You can calculate the odds of getting disease given that you're exposed to the risk factor versus not, right? So that would be like 50 divided by 20 over 100 divided by 130, right? And in fact, by definition, I'm going to use some notation here, introducing some probability symbol here, right, and explain the odds. So P1, the subscript 1, indicated that you're exposed to risk factor, right? So the probability of exposed to risk factor is called P1, right? And that's when you're in the row 1, right? You're exposed to risk factor. The P1 is the probability of success, and here is probability of getting 1 from disease data, which is yes. So P1 denote the probability in row 1, right? 1 stands for row 1 to have disease. Okay, that disease status is 1 or yes. And 1 minus P1, of course, is the probability of not getting disease given that you're exposed to the risk factor, right? So 1 minus P1 is yes, if you're exposed to the risk factor, the chance of no disease. Okay, and then so O plus here stands for odds of getting disease, right? That you're exposed to risk factor. So the O plus means you're exposed to risk factor, right? So when you're exposed to risk factor, what's the odds of getting disease? That's really this P1 over 1 minus P1, right? That's actually 50 over 70 divided by 20 over 70. Okay, so that's calculated over here, 2 over 5. But since you have the same denominator, so usually we just say the odds of getting disease for exposed to risk is 50 over 20, right? Because the denominator is canceled. The same thing for the second row. If you're not exposed to risk factor, I use O minus. If you're not exposed to risk factor, the odds of getting disease, we can say is 100 over 130, right? And for the disease status, again, 1 is 100, and then 0 is 130. So you remember this, right? And in fact, the way we define odds really is the ratio of conditional probability, right? Probability of getting disease versus probability of not getting disease. Ratio of that is the odds of getting disease, right? So here, this is O minus is odds of getting disease if you're not exposed. That's O minus. O plus is if you're exposed, right? O minus is if you're not exposed, the odds of getting disease. So ratio of these two numbers, right? Odds of getting disease if you're exposed to a risk factor versus odds of getting disease even you're not exposed to a risk factor. Ratio of that is the odds ratio in this case. It tells you the odds of having disease, right, giving you exposed to the risk factor versus not. Okay, and that number is odds ratio. And this number is different from relative risk. So it's very important that when you're trying to interpret this odds ratio, right, this number 3.25, you can say this is odds of getting disease, right? For exposed to a risk factor, it's about 3.2 times than the odds of getting disease given that you are not exposed to a risk factor. That's the meaning of this. You don't want to say that this odds ratio is 3.25. So you're going to say if you're exposed to a risk factor, you are 3.25 times more likely than those who are not exposed to a risk factor. You don't want to use that term, right? 3.25 times likely, because it's not exactly 3.25 times likely. If you want to use this term, you got to have a ratio of probability, not ratio of odds. Odds ratio is ratio of odds. Okay, so keep that in mind. That's very important. A lot of time people interpret it the wrong way, right? You can say, well, if you're exposed to the risk factor, you're more likely to get the disease than you're not exposed, right? And the odds ratio of that is 3.25. That's a proper way of saying it. But you definitely don't want to say if you're exposed to a risk factor, you're 3.25 times more likely than to get disease in non-exposed to risk factor. I hope it makes sense to you, right? It's very important. Odds ratio is different from relative risk. Okay, so that's the odds ratio, and of course that number theta here denotes the odds ratio, right? If odds ratio is greater than 1, that means what? In this case, you're exposed to risk factor, you're more likely to get disease. If this odds ratio is less than 1, that means what? If you're exposed to risk factor, you're less likely to get disease, right? And if this odds ratio is equal to 1, that means, well, the risk factor is not a significant factor. Either you're exposed or not exposed to the risk factor, the outcome is about the same. Okay, so odds ratio, you got to know that, right? We learned that before. And you also remember there is a confidence interval estimate for odds ratio formula, right? We did that earlier. Okay, so once you calculate odds ratio, with the data, you can also compute the confidence interval estimate for odds ratio. And again, if you look at that interval estimate the odds ratio, if that interval doesn't cover 1, it covers a range of number that is higher than 1. That generally means what? If you're exposed to risk factor, you're more likely to get disease than those who did not, right? If this number covers a range of value that is between 0 and below 1, that means if you're exposed to risk factor, you're less likely to get disease, right? So hope this makes sense to you. This is something that we did before, studying the odds ratio. Okay? And 1, remember that's a magic number, just like studying relative risk too, right? If that number is 1, that means risk factor is not a significant contributor, right, to the outcome of having disease or not. Okay. Okay, so that's important, right? So I'm gonna use this example. It's a famous example when people talk about logistic regression, right? The example is about modeling dengue disease, right? It's a disease spread by mosquito bites, right? And you get fevers and all that. Anyway, so the data I have here have several variables. Age is a quantitative variable, age in years. And we have socioeconomic status. 1 stands for upper, 2 stands for middle, 3 stands for lower, right? So a lot of times when you get data like that, the data will code as a number, right? And also which sector you live, right? Maybe you live in sector 1 and sector 2, so different area. And disease status, this would be a response variable, right? You want to model the disease. 1 stands for yes, the person have disease. 0 means no disease. And there's another nuisance variable here is that saving accounts data, whether you have saving account or not. 1 stands for yes, having saving account. 0 stands for no. Now, sometimes data comes in just in this numeric value, right? So if you run the R commander, if data really comes in this numeric form, right, like socioeconomic status 1, 2, 3, you got to make it a factor variable, remember, right? And we want to run a regression, logistic regression. It's a regression. So the way you treat the categorical variable will be the same as the way we treat categorical variable when you run multiple linear regression, which we just went over. Okay. So this study actually is trying to model the dengue disease. I try to find what actually is a significant contributor to the dengue disease. So having disease or not is the response variable. In this case, the response variable only has 2 values, 1 or 0. Okay, not like the simple linear regression. So you cannot use a simple linear regression to model this data. Okay. Before we run the analysis, we can actually look at the odds ratio, right, in this study. So using sector as a variable. Sector is a predictor. Okay. We run the data. There are 196 pieces of data, and this is the distribution of the data cross contingency table. So from this table, the odds of getting disease for sector 1 is 22 versus 95. For sector 2 is 35 versus 44, right? So the odds ratio is 0.291. So you have a number that is less than 1. That means what? If you live in sector 1, you're less likely to get disease, right? Of course, people usually like to look at the other way, right? I just take the reciprocal. I can find the odds of getting disease for sector 2 versus sector 1. If I do that, really just a reciprocal of this number. This number divided by 1 over that number is this 3.45. So if you make your number in this way, then you can say if you live in sector 2, your odds of getting disease is 3.45 times than that you live in sector 1, right? That the people will get disease in sector 1. The odds of getting disease in sector 1. Okay. So a lot of time people like to do it this way. If when you find a number that is fraction less than 1, you just flip then, right? You can say one sector, live in one sector, your odds is this many times than the odds of getting disease in living in second sector. Okay. So that's good, right? So you know that. Now, actually, when we run the regression analysis, you will get these type of number later on because that's one of the results. That's also what makes this logistic regression so popular when it comes to modeling the categorical data. So what is the logistic regression? A logistic regression is the regression method that we use to model binary response variable. Right? So your response variable has 2 categories. Right? And your predictive variable, just like multiple regression, you can use a quantitative or qualitative predictive variable. So, but the response variable is binary, so that's very important. And usually the response variable is coded as 1 or 0. 1 indicate a category of interest. So here you try to model the chance of people have disease. 1 indicating disease, 0 indicating no disease, right? So when you observe a set of data, right, observe a group of subject, now you're interested in whether the subject have disease or not. That's 1 or 0, right? So every time you observe a subject, there are 2 possible outcomes. Now, this kind of variable has a typical distribution associated with that. I wonder if you remember in the earlier chapter when we talked about probability. The variable like this has a Bernoulli distribution, right? Of course, then you have observed a set of subjects and you're interested in how many of them have disease, that becomes a binomial experiment. Okay, but the variable here, for modeling a person who have disease or not, and that variable itself, just for one subject, has a Bernoulli distribution. They only take a 1 or 0. That's a response variable. Okay, and in the Bernoulli distribution, the important parameter is what's the probability of success. In fact, logistic regression is really for you to model that probability of success. Okay, so we did simple linear regression earlier. And when we do simple linear regression, we can do a scatter plot like this. Right? We have both quantitative variables, so we can see a linear trend. Then we decide on how we fit the data. We use a regression line that actually help us to predict or estimate the location, the average response, right, for any fixed level or predictive variable value. That's what we do in simple linear regression. And we have such an assumption, right? We have an error, normal random error with constant variance assumption when we try to predict the average response, right, using a predictive variable. That's when we do simple linear regression. And our data look like this, right? If you look at this direction up and down and any fixed section of this predictive variable value, it's kind of uniform and have same kind of spread and bell-shaped distributed, right? But if you try to model the outcome that is binary, 1 or 0, right? The relationship between the average response and then the predictive variable value would not be linear, right? So it's going to be hard for you to figure out this term, right? This deterministic model in the regression. Okay. This is a typical example. Response variable has 1 or 0, and you have an experiment variable is quantitative. If you want to do a scatter plot, it's going to look like this, right? It doesn't look like a linear trend. And so it'd be questionable if you try to fit a straight line and try to model this data with a straight line, right? So linear regression is really not going to fit this data well, okay? But remember, when we model this binary outcome, right, the outcome actually has a Bernoulli distribution, right, in just each subject, right? And we're interested in probability of success. And we try to model the probability of success, right? So actually a reasonable, actually this is just a quick review of what we learned earlier about the Bernoulli distribution, right? And this slide just telling you that when we try to model the average response, we really model the average of Bernoulli distribution, which is the probability of success. Okay, so we want to come up with a good model, actually can fit our data and also be a good estimator for estimating the probability of success. Of course, this straight line is definitely not a good idea, right? If you fit this straight line, you're not going to satisfy the linear regression model, the assumption, the uniform variance and normal spread of the variability of response variable. You don't have that. You don't have constant variance, right? You can have all kinds of problems. Okay, so the better one to actually model this data is, since you're modeling the probability of success using this data, right? And the outcome is actually categorical, binary. We have a lot of successes here and then a lot of failure here. So if a model is for modeling probability of success, it makes sense to fit a curve like an S-shaped curve like this instead of a straight line. So over this region, you have more data point that is low, at 0. And over here, you have more data point that is close to 1. Okay, so over here, the probability of success of getting a 1 be smaller. And when you go further and further towards right, the probability of success get higher and higher. And then eventually it approaches to 1. Right? So an S-shaped curve is a better curve to fit the model for predicting probability. So in fact, what's that F-shaped curve? F-shaped curve, for fitting that F-shaped curve, actually it has this specific function called a logistic function. Right? That actually has a nature like this, a behavior like that. That will fit our data better, in better sense, right? And actually meaningful for predicting probability of success. So this becomes our model. Okay. This is a simple example with one predictor and has a positive correlation. So when the predicted variable value increase, the probability of success increase. So that means you have a positive correlation. There could be a negative correlation when the predicted variable increase, the probability of success decrease. So there may be a situation like this. Right? This is just a typical example. But the actual outcome of the prediction model for probability of success would be this formula. And there are two forms. You can write it in this form or this form. Okay, so this becomes a model. Instead of y equal to alpha plus beta x, right? This becomes a model. If we want to predict the probability is equal to exponential function of alpha plus beta times that predicted variable over 1 plus the exponential function of that expression. Right? That becomes our model. And of course, we will use the software to help us to estimate the alpha and beta, so we will get a model. Right? So that's a model we have when we run logistic regression. Okay, this is a different form of that model. If you try to solve for this alpha and beta, right, or solve for log of odds, look at this probability over 1 minus probability. This is actually log of odds, right? So natural log of odds, actually, that's another expression for this probability model, right? We can write that model in two forms, at least two forms. One form in this and one form in terms of log of odds. Why do we want to do this? Because if you see, it's very interesting. If you try to model the log of odds, it's a linear function of x, right? So the model becomes something that's similar to you're familiar with, okay? And how do you interpret the beta here? Beta is the rate of change of log of odds per unit change of x, right? And beta also, its sign help us to see whether there's a positive or negative association between the predicted variable and log of odds of success. Okay, so that's really an interesting model. Okay, and this model is very useful, in fact, nowadays for predicting, modeling the categorical response variable. Okay, and so if I take exponential function of this expression on both sides, actually can the model become a model that help me to model the odds, right? Take away log, right? That means that I have exponential function on both sides. The odds of success can be estimated by exponential function of alpha plus beta x. So there are different ways, right, to write this model. It depends on the application, though, right? And then if you solve for p again, you go back to that first term. So this is just telling you that they all same model but written in different form. Okay, and of course our goal when we do the modeling is estimating the alpha and beta, and there are approaches like maximum likelihood estimation approach that can help us to estimate these alpha and beta. As far as what's the maximum likelihood, well, you got to have some kind of more theoretical statistics class to really understand what it means, right? By this point, it's just some estimator that maximizes the chance of evidence to occur, right? If you can come up with estimator like that, that's a good estimator, okay? And so once you found this estimator for alpha and beta, you have the model now, and that model can help you to predict the probability of success, okay? So what you do then, if your predictor variable is like a sector, right? If your predictor variable is leaving sector 1 or sector 2, let's say sector 1 is 1, sector 2 is 0, then once you found a model for estimating alpha and beta, found a model, you can just plug in 1 or 0 to predict the probability of getting disease or not getting disease, right? I hope that makes sense. All right, we will see some examples there. So here again is the outcome from SPSS. All right, so it's good to know this, and then later we're going to also run the R commander for it. Okay, so in SPSS, when you run this, if your data coded as 1 or 0, 1 or 2, or any numbers, there's a function for you to actually categorize your data, right? So here indicating that sector 1, you have an indicator here, 1 indicating sector 1, 0 indicating sector 2, right? And in R commander, you can do the factor, right? Convert a numeric variable to factor. And or when you read the data, it is already categorical variable, then R will treat the data value that is a higher level of alphanumeric order. That order is like A, B, if you have letter words like A, B, C, D, right? A is all lower rank, B is next higher rank, and so compare A with Z, Z is of a higher rank, right? So if you're sector 1 and sector 2, you put it as like a yes or no, for instance. Yes, sector 1, and no for sector 2. Yes is of a higher rank. Usually we have higher rank, it is considered 1, and lower rank considered 0. If you have R commander to set up indicator variable for you, right? It's almost like 1 and 0. Okay, if you're a binary variable, we will look at that in a little bit, right? So I just ran the logistic regression with sector variable in there, and I got this outcome. There's a constant. This is similar to the outcome from simple linear regression. You have this B, that's those beta estimate, right? You have also this SIG. These are SIG, which is the test for significance of the factor variable. And that actually has a p-value so small, that means what? The sector variable is significant. And this sector variable, parenthesis 1, is an indicator variable indicating living in sector 1. Right? Remember that? Okay. Let me go back to this. We have SPS as set of indicator variable 1 indicating sector 1, 0 indicating sector 2. Okay. So over here, the p-value is so small, so I'm going to say the sector variable is a significant factor. Okay. Then we can pull these information down, and this constant here is the alpha hat, and this next number next to sector is the beta hat. So we have alpha and beta hat. We can put it in that probability prediction formula to predict the probability of success. Right? The model is predict the probability of getting value 1 for the response variable. If value 1 indicating having disease, then this model will be the probability of getting disease, right? And X in this case is a sector variable. 1 indicating living in sector 1, 0 indicating living in sector 2. So if I plug in 1 here, calculating this formula, I get the probability of getting disease if you live in sector 1. If I plug in 0 for X, I get the probability of getting disease living in sector 2. So you can get the probability estimation, right? For any time you have a subject coming, you can predict the probability of this person will get a disease or not, right? Or how likely this person will get a disease. Okay. So this is a simple logistic regression model with just one predictive variable. Okay. And it can help us to also figure out the odds, right? If you know the probability, then 1 minus that probability is the odds. You can also estimate the probability of odds, right? And you can also estimate the log of odds. So whichever form you like to find out, right? You can use it. Since you get the probability, right? You can find the probability. You can predict the probability of odds. You can estimate the odds. You can estimate the log of odds, right? Whichever you like to do. Right? So this is kind of an example for estimating odds. Right? Now, what's so good about estimating odds? If you estimate odds for people living in sector 1 and for getting disease, and get the odds for people living in sector 2 to get the disease. Ratio of these two will be the odds ratio. Okay, so you can get the odds ratio for people for getting disease living in sector 1 versus sector 2 by using these two numbers. Right? However, if you run this analysis, you don't really have to calculate this one by one. One of the output allow you to actually get the odds ratio. And that odds ratio is actually very easy to get, right? The odds ratio will be just exponential function of beta will give you the odds ratio for each of those predictive variable that you use. Right? The idea is this, actually. For those of you who remember the log function, if you can't remember it, just listen and then pretend that you understand. It's okay. Right? Log of odds, all right, we say the log of odds is a linear function of x. This is another form of that model from logistic regression. And so the beta is rate of change, in this case, the rate of change of log of odds per unit change of x. Right? Now, if your x is indicator variable takes on 1 or 0, right, then rate of change of log of odds per unit change of x, right, this is actually that rate. Right? When your x is 1, that's a log of odds of x is equal to 1. And when x is 0, this is log of odds when x is 0. Right? And the difference of this really mathematically, by definition, log, right, is really log of odds ratio, right? And log of odds ratio actually give you what? The beta, which is really the coefficient we estimate. If I both sides take exponential function, okay, then you get the odds ratio is equal to exponential function of beta, okay, which means if you want to get the odds ratio, once you have beta, just take the exponential function of beta, you get the odds ratio, okay? Which means in this particular case, when we try to estimate the beta is negative 1.234. So exponential function of beta give me 0.219. If you remember the output the thing that I calculated earlier for odds ratio for the data, let me go back very quickly. Odds ratio for the data, oops, it doesn't let me go back. Remember this number, 0.291? That's odds ratio for living sector 1 versus sector 2, right? Odds ratio of getting disease living sector 1 and sector 2. We actually got it from the logistic regression. Okay, so this is just to tell you now you can get the odds ratio from the logistic regression output if you know the estimate of beta. Exponential function of beta is the odds ratio. And of course, the reason we can do that because we test for odds ratio of beta equal to 0 or not. Beta is not 0, right? So then this odds ratio makes sense, right? If you test for beta equal to 0, like in this here, if you test for beta term equal to 0, that means in this case it's a sector variable equal to 0 or not. I'm sorry, not equal to 0, equal to 1, right? If, equal to 0 is odds ratio equal to 1, right? Testing odds ratio equals 1. You get the p-value that's so small, that means what? Odds ratio is not equal to 1. That also means that the sector variable is significant. In fact, if you look at this output, there's an exponential function b. That's really exponential function of this. This number 0.291 is actually taking exponential function of this negative 1.234. You get that. So when you run the analysis, actually software will produce this exponential function of beta for you. You just need to know where to look for it, right? You don't have to do the computation like I shown you in the slide. Try to calculate it. Odds ratio. You don't need that, right? It's in the output, right? My slide just explained to you why exponential function of beta is the odds ratio, okay? And you can get that from the software, okay? And in fact, software will also give you the confidence interval estimate for odds ratio. So if that factor is significant, you're going to have a confidence interval for odds ratio that cover a range of number that doesn't cover 1, right? Because if it covers 1, that means what? The risk factor is not a significant factor, right? So that predictor is not significant. Okay. So this is actually the confidence interval estimate for odds ratio for living sector 1 versus sector 2. Now, what if I want to find an odds ratio for getting disease for sector 2 versus sector 1? For odds ratio itself, you take the reciprocal, right? How about for confidence interval? You just take the reciprocal of these two numbers and switch the position. You get the confidence interval estimate for it. So you get 1.81 and 6.54, and I think you saw that earlier in the previous slide. You get that too. Okay. So once you have the output, SPSS output, if you also ask for confidence interval, here I do have a confidence interval estimate for odds ratio. So you get them all. However, in ART Commander, you have to take an extra step to get the confidence interval estimate for odds ratio, right? And I will show you how to do that. Okay. So, and then this is a situation that if I actually include not only just one, but several variables, and among those variables, I have a socioeconomic data, so, and it's a categorical, so I have to set it up and make it a two indicator variable to represent the 3 category socioeconomic status in the model. So this is just showing you how SPS is doing it. Right? So the parenthesis 1, this variable for indicated upper socioeconomic status. Parenthesis 2 has an indicator indicating middle class, right? And so if you don't, if lower level didn't have an indicator variable, that means lower level is so-called a base class, right? Socioeconomic status, remember we code 1 for sector 1, and then 0 is sector 2. So the sector 2 becomes a base class. Base class, when you try to calculate odds ratio, there's a base, right? You're comparing with people who live in sector 1 versus sector 2. So odds of sector 2 is in the denominator, right? Odds ratio in sector 1 is a numerator. So whatever that odds in the denominator, that's a base class. And you're comparing odds for that sector 1 versus its base class, right? And for upper, for socioeconomic data, when you run the logistic regression, you're going to get estimated for parameter for beta 1 and beta 2 for upper and middle level. You take exponential function of these beta, you get the odds ratio. How do you interpret the odds ratio? The exponential function of beta for that beta associated with the upper give you the odds ratio for getting disease for upper class versus lower class. The exponential function for beta associated with middle class will give you the odds ratio for getting disease for middle class versus lower class. So lower class is like a standard you're comparing with, right? So lower class is so-called a base class. That's the kind of term that people use, right? So in the sector situation, sector 2 is a base class. I hope when I mention base class that you understand what I mean, okay? So look at this output. This is the output. You get these odds ratio, right, from the socioeconomic status. This is 1 and 2. So this tells you that if you live in sector, I mean, if your socioeconomic status is 1, which is high, versus low, right, the odds of getting disease is 0.757. That means if you have higher socioeconomic status, you're less likely, the odds is smaller, so you're less likely to get disease than the lower class. This is odds ratio comparing with middle class versus lower class, right? So if you're in middle class, your likelihood to get the disease is less than lower class. However, if you look at the p-value, these p-value are not less than 0.05. That means what? These are just coincident, right? Next time I get the data, I may get 1.7. Okay, so you don't really need to interpret these numbers. I'm just interpreting this to help you understand these numbers, the meaning of these numbers, right? But if you do find out that statistically these factors are not, socioeconomic status is not significant, then there's no sense to interpret the odds ratio. Okay. But the sector is still, right? Sector has a p-value of 0.001. That means what? Sector is a significant factor. If you live in sector 1, you're less likely, your odds is less, right, to get disease and live in sector 2. Remember, sector parenthesis 1 is an indicator variable indicating sector 1, right? And sector 2 is a base class. I also have this savings, and saving actually is a variable that takes on value 1 or 0. But if you didn't categorize it, just leaving in 1 and 0, that is okay because 1 and 0 itself is already indicator variable. Right? That's actually exactly what it is, the kind of value you use when you really run that regression model. Okay. In practice, when you really run the regression model, the software or the system or the algorithm actually deal with value. They don't deal with like a upper, lower, middle, socioeconomic status. Right? They only look at number, 1 or 0, 1 or 0. Okay. We also have this age variable, and age variable has a p-value of 0.003. That means age variable is also a significant factor, right? And look at this coefficient here, 0.027. That means what? There's some kind of positive correlation. When age increases, right, the chance of getting disease increase. Okay, the odds of getting disease also increase. And with the odds ratio 1.027, that means what? If you compare two consecutive age 20 versus 21, right? 21, the odds of 21 to get disease versus age 20 to get disease, the odds is like 1.027, right? Seems like a little bit small. You want to compare two age group that with a higher difference, maybe age 30 versus 20. That would make more sense than compare two age group, two age class that are so close to each other. Okay, and this is a slide just if in case you drop all these insignificant predictor and just remain just only significant factor, right? Then you will have a model only have these two variables in there. Okay, and you can write a model actually like this model there. You can write a probability prediction model like this one here, right? Similar to this one, except for the expression here, you got to add one more term, right? You have alpha plus beta 1 x1 plus beta 2 x2. That would be the difference. This is a situation that had one predictor. If you have more predictor, you have to extend this one. Okay. So for this particular example, you're going to have negative 0.978 minus 1.181 times sector variable and plus 0.027 times h variable. All right. For that exponent, you got to have that whole long expression. Okay. Then now, since these p-value for these particular factors, they are significant, then you can interpret these EXPB means odds ratio, right? So this is the odds ratio now. This is actually odds ratio for people who live in sector 1 to get disease versus sector 2. So sector 1 is less likely because its odds ratio is less than 1. And you found this odds ratio is different from what you just got earlier, right? Why? Well, because you have added an H variable in the model. So you can do the odds ratio estimation with H variable control, right? Or adjusted for. Okay. So when you run it, remember when you're doing the analyzing the observational data from observational study, there are always possible confounder that may mess up the whole thing, right? You may have uneven distribution in age, right, among these people who live in two sectors. So that will make the comparison unfair. But if you include the age variable in your model, then you have age variability due to age adjusted for, right, or controlled. So that will make the comparison of a chance of getting disease between two sectors more meaningful or reasonable. Okay, hope this makes sense, right? That's a good thing of having being able to take the regression approach. And this following example is just explain the odds ratio, right, for odds ratio value for a quantitative variable. Right? You can actually, as I said, you can actually use it to compare different age group, right? Estimate the odds for different or probability for each different age group, and compute the odds ratio for them. Okay, you can do that. Right? But I don't think I asked you to do that. Right? But you can do that by looking at the output of the data. Okay. When we run the model, right, there's always a model checking. When we do simple linear regression or multiple linear regression, we check normality, right? And the logistic regression is somewhat like a non-parametric test, almost. So you're dealing with the frequency, right? So there are different ways we check how good the model fit the data. And there's this so-called Hausman-Lerman-Show test that can help us check how well the model fit the data. And this is a really rough model checking method. There are other methods out there now that would do a better job, right? And in this class, I'm just touching this, just to give you a general idea, right? That you got to check them how well the model fits the data before you decide to use the model. And this Hausman-Lerman-Show test is a goodness for fit test, testing whether the model fit the data well or not. Now hypothesis, of course, model fits the data, right? Alternative is not. So if you have a p-value so high, higher than 0.05, that means the model is reasonable. You have no significant evidence enough to reject that model to a good fit, right? So if you see a p-value that's higher than 0.05, usually we suggest that the model is doing okay. And so this is actually just another example. It's a split contingency table. So you want to model low birth weight. You can using a mother smoking or not as the predictor variable, and also parity means whether the kids is a firstborn or not, right? As another predictor variable. So you have two categorical predictor variable, and the outcome is also binary. Logistic regression deal with binary outcome, right? Whether you have a low birth weight or not. So you can model the data, right, using two categorical variable to model a binary categorical variable. Okay, and this is just the coding, right? The low birth weight coded as 1 for low birth weight, because low birth weight is really what we're concerned about, whether a mother will give a low birth weight baby or not, right? And then for parity, 1 indicating yes, firstborn, and smoking, 1's indicating yes, mother smoke. Okay, so you always want to know the indicator indicating what, right? What category? Smoke or not smoke, parity or firstborn or not firstborn. So you got that now, right? So I just ran the logistic regression and got this output. I didn't have to set up a categorical variable because I have those variables already as the indicator variable 1 and 0. That's good enough, right? So over here, the parity, I give the p-value 0.1, so which means what? Firstborn and not firstborn doesn't affect the birth weight. But mother smoke, yes, it does affect. It's significant. Okay. And remember, for smoke variable, 1 indicates smoke, 0 indicates not smoke. So this is an odds ratio of 1 versus 0, right? For having low birth weight. So when you look at this number, you will know that the odds of having low birth weight baby for smoking mother is about 3 times than the odds of those who are non-smoker. Right? So if you're a smoking mother, your odds of having low birth weight is much higher. It's 3 times than the odds of a non-smoker. Okay. And so that's really a good number to present, right? While you've done your analysis, you can always explain to people what's the odds ratio are, right? To help people to understand how significant a risk factor is. Okay. This is just another thing that involves interaction terms, so I think I can kind of skip that, right? And I hope I have time to run the logistic regression, right? So we do have time. So how do we run logistic regression? Comment. Okay, good. R commander, right? I'm going to open that file data. I think I have Excel file, right? Do Excel data. I can remember this is LR stand for logistic regression. Okay, can look for that data. Disease. Right? This is about modeling dengue disease. I'm going to click on. Oh, I clicked on the wrong thing. Cancel. Import Excel LR. Download disease. Okay, and let's take a look at this disease variable. So I have, look at here, I have disease that is 1 or 0, okay, and sector 1 or 2, and socioeconomics 1, 2, 3. So these are quantitative, they are not qualitative, right? So if you just run a logistic regression using disease and pick these 3 variables and run it, you're going to be in trouble because sector is 1 or 2. That's not categorical. Okay. You can run it, but the outcome will not be correct. So what you need to do is go to measure variable in active data set, convert numerical variable to factor, right? I have socioeconomic status. Click on that. I'm going to label. So 1 actually is for high, 2 is middle, 3 is low. Okay, so that's what originally the data is coded, right? So I click OK. Look at my data. Now it's set, right? And sector, I also have to make it factor. I also want to label them. So for sector, click sector, and 1 is sector 1, right? And 2 is for sector 2. Okay, and click OK. Right. And I also have, I think I have saving account variable, don't I? Yes. Well, I did not put the saving account, so that's fine, right? Saving account is not really meaningful anyway. Okay. So I'm going to run the analysis. I didn't set up let me go back. I didn't set up the disease variable. So the model is, remember that model is for estimating the probability of getting 1s for the outcome variable, right? Probability of success. 1 is indicating success, right? So in the data, 1 actually indicating people have disease. So once you come up with a model, the model will be probably getting 1s or probably getting disease, right? So what I can do now is I want to run the model, click statistic, fit model, generalized linear model, right? Logistic regression is one of those models fit into the generalized linear model, right? Set up. And then your outcome variable, response variable is disease. You want to model the disease using age and socioeconomic status and which sector you live. I just keep clicking it, and it will just put them in there. And just keep these options the same. Right? We want a binomial and use a logic. Right? The actually logistic regression model that we mentioned is actually use a logic function that log of odds. That's equal to, actually, I'm sorry, the probability is equal to logic function. But anyway, I'm going to click OK. It's modeled by that logic function. Right? So around the regression, here is my results. Here is the resulting coefficient here, right? Age positive correlated. These are the middle versus low. Now in our my lecture note, I had high and middle. Okay. Now in our commander, it'll always use the lowest rank of data value as the base. Okay. So I have high, middle, low. High start with H, right? So H in alpha numerical order is lower than M and L. So H high is the base variable, right? So once you get these numbers, right, these exponential function of these give you the odds ratio for comparing middle class with high and low class with high. And also here, sector 2 is higher than 1, right? So 1 becomes the base category. So this will be actually for accessing the significance of sector variable, but when you get the odds ratio, it's the odds ratio living in sector 2 versus sector 1. And also look at these are the p-value, right? These are the p-value helping us understand the significance of these variables, and only age and sector variable are significant, just like what we had earlier. Okay. Now you might wonder, well, how do I get the odds ratio and the confidence interval estimate for odds ratio? Well, we have the GLM.5. This is the model we have there. We can click on model to get those estimates. Click on model, come to confidence interval. Click on confidence interval. I want a 95% confidence interval. Click OK. I got actually, let me make this table smaller. Right? Here is the confidence interval estimate for the parameter themselves, and also the estimate for the parameter. But the next section is exponential function of those estimates. These are the odds ratios. So let me make this table a little bit smaller. I mean the screen a little bit smaller, so the outcome will really fit in there. Let me do this again. Right, so they're all here. This section here, right? This is exponential function of estimate. So this telling you that these are the exp of beta, exponential function of beta, right? So if you live in sector 2, your odds are like 3.45 times than those in sector 1 for getting disease. And this would be confidence interval estimate for the odds ratio of getting disease living in sector 2 versus sector 1. Okay. And this is for middle class versus high class. This is lower class versus high class, right? And these are the odds ratio. Okay. If I say I insist I want to see the output just like a SPSS, right? How do I do that? We can do that. If you click on data, manage variable in the active data set, and go down to reorder factor level. Click on that. want to reorder socioeconomic status. Let's click on socioeconomic status and click OK. And yes, I want to override variable. Now, you see, high is ranked the lower, the 1, right? So I make that 3. Make the lower class 1. If you do that, the odds ratio will be high versus low and middle over low, right? If you estimate the odds ratio, I click OK. Also, for the sector, I like to do it the same way as what I saw in SPSS. I reorder the sector. I'm going to make sector 1 the 2 and the 2 the 1. Remember, the smaller value is used as a base category. So if you do it this way, you will get the odds ratio for sector 1 versus sector 2 to get disease. Okay, so I click OK. And then let me rerun the analysis, fit model, generalized linear model, same number there. I click OK. I get the new result here, right? You see the sign changed, right? If I run the odds ratio estimation, look at the odds ratio, they all become positive, right? And this is 2.02. Well, number seems like it's off because I actually adjusted different. So I'm sorry, I didn't add the what's the other variable? Saving account variable. So the outcome is slightly different, right? But we can compare this model with those that don't have the socioeconomic status. Okay, maybe we run the model with only 2: fit model, generalized linear model, and then only sector and age. I click OK. And if you compare this table with a table would have 0.026 and negative 1.18, 0.027, all right, 26 and round to 27, negative 1.18, right? So once you reorder those categorical variables, you can produce the same result as what you saw in SPSS, right? So those order matter. The order decide which one is your base class. Okay. Does it make sense? Right? And you can also click model and then graph and to do some basic diagnostic. And usually the graph will look kind of weird, right? And normality plot is not really right there. Right? This is a generalized linear model. Actually, there's also model diagnostic. You can check on variance inflation factor. I think I forgot to mention this when we run the multiple regression, right? The same thing when we try to run the multiple regression. Remember, we mentioned about variance inflation factor. You can do the same thing, right? To check the VIF. That's a VIF score. I'm glad I did that, right? We didn't do that in that multiple regression, linear multiple regression thing. This helps you to check whether they are predictive variables that are closely related to each other that create collinearity problem. Right? I think, let me go back to that data set. That was data set 2, I think, right? Let's go back to that data set. Yes. Right. If we run this regression, statistic, fit model, regression, we try to model the weight using age and height maybe, okay, and click OK. So we ran the regression, right? And you want to check for multicollinearity, click model, numeric diagnostic, variance inflation factor. You get the variance inflation factor there, right? They're all less than 4, less than 10. So there's no variance inflation or collinearity problem. Okay, I forgot to mention that earlier, but I'm glad I caught it. So this is a place that you can check for VIF to see whether there is collinearity problem. Right? The general guideline is no more than 10. If this thing passed 10, that's bad. Now some of the people doing, a lot of people doing social science research, they use 4 instead of 10, right? So using a more stronger restriction, so you have more than 4, then you consider maybe try to do something to fix the collinearity problem. It depends on the objective of the research, the study. Sometimes people insist to use all these variables that are somewhat dependent, correlate to each other. There are ways to adjust that, right? But that's not what we're going to talk about in this course. Okay. So, any question? Do you have any question? Okay. On Springboard, let me see, do I have Springboard? Okay. On Springboard, I made a note here. Logistic regression, YRB example. Okay. That's the kind of exercise probably like you to play with if you have time. All right. I have this as R data. So if you download it and load it from R Commander, it'll load the whole data. And this is actually a sample from the use risk behavior study. And it has a variable that is used marijuana in the past 30 days or not, and then other predictor variables, right? So I ran a regression analysis and come up with this odds ratio estimate, and with these as the variables, right, that I have in the data. So you see G4. G4 is what? Are you Hispanic or not? When you see a T no, that means what? You have a G4 indicator variable indicating no, right? So you have an odds ratio here. This odds ratio is if you're not Hispanic, your odds of using drug versus if you are Hispanic. Okay. And so here 83 T no, 83 is this question, participate in sport, more sport team in the past 12 months or not. And it indicates no. That means what? If you did not participate, right, and your odds of using drug versus those who participate. And that's kind of weird, huh? Another thing I forgot to mention is that you can also, in my data, I did not recode the disease variable. It stayed as 0 and 1. Okay, so remember the model is for predicting 1 for response variable. Now, if you code it as yes or no, yes is of a higher alphabetical numeric order than no, right? So yes automatically will be considered 1 and no will be considered 0. Yes is of higher value, higher rank. Okay, just in case you really actually recode the disease variable into yes and no and make it factor variable. As long as a factor variable, if it's two variable, right, in two category, the higher value will be 1 and lower value will be 0. Right? Higher rank will be 1, lower rank will be 0. So yes will be 1, 0 will be. I can do that. Right? Let me do that very quickly. Data, convert numeric variable, disease status. 0 means no, 1 means yes. Right? If I redo that, I can still run the model, statistic, fit model, statistic, fit model, general linear model, and I pick the disease knowledge factor, right? Put it in here. And then socioeconomic status, sectors, and age, whatever. And if you run it again, you're going to get the same result as if you have 1 and 0 for disease variable. Okay. So just in case your variable already is a factor variable in R Commander, you can still run it. Make sure, right, you know the structure or the how you define these variable while you're interpreting these numbers, right? You can easily make mistake, right, if you was